In this video, we'll review the different types of chi-squared tests. On the AP exam, one of the easiest ways to identify a chi-squared problem is because you're going to be given a table such as this one right here. Often it's also going to be accompanied by some kind of prompt saying, is there sufficient evidence or does the data support the conclusion that ... And what that's asking you to do is to do a hypothesis test, either a chi-square test of homogeneity, chi-square test of independence, or with situations that look a little different than this one here, a chi-square goodness of fit test. So here we have a simple random sample of adults from a large city. They recorded the age and annual income of each adult and organized it into this table here. So we'll start off with just some basic probability problems. What's the probability that a person chosen at random from those in this sample will be in the 31 to 45 age category? So we are looking at this row right here. That's our 31 to 35. In particular, this value right here is the sum of everything in that row. And that's just going to go over top of the total number of people in the table, which is in that bottom right corner. So we have 89 out of 207, which is about 43%. Part B, what's the probability that a person chosen at random from those in the sample whose incomes are over $50,000 will be in that same 31 to 45 age category? This is a conditional probability, and its condition is given here. Their income is over 40,000. I'm sorry, over 50,000. All right, so that's going to restrict what we're looking at. So for this problem, instead of looking at all 207 people in this table, we are looking at this row, just the people who make over 50,000. There's 96 people in this row in total, and of those 96, 35 are in that age group. Right, so 35 over 96 would be our fraction, giving us 36.5%. Also, let's just take a minute to identify the different notations these are written in. So if you were given a problem like this, find P of 31 to 35, it's just finding the probability that someone is in that 31 to 35 age group. This line right here in the second problem means given. Okay, it means that this is a condition that needs to be met. So we're only looking at the people in that over 50,000 age group, and then within that age group, we're finding the probability that they're 31 to 45. Now, based on those answers, is annual income independent of age? Explain. Now, if two variables are independent, it means the probability of one doesn't affect the probability of the other. And in this case, it would mean that the two probabilities that we found in part A and part B would be essentially the same. So no, they're not independent. If they were, the two probabilities would be approximately equal. It appears that there's an association between age and income, and being in the 31 to 45 age group makes you less likely to earn over 50,000 compared to the overall population. So the overall population, 43% are in that 31 to 45 age group. However, once we look at only people who make over 50,000, only 36.5% are in that same 31 to 45 age group. So you're less likely to be in this age group if you make over 50,000, at least compared to the overall population. Now we can answer that independence question with a hypothesis test, which we're going to do on the next slide. But before we do that, let's just refresh on how certain components in that test are calculated. So when we're given a table, all right, we'd be dealing with either a chi-square test of homogeneity or a chi-square test of independence. When I say a table, I mean a 2x2 table. Okay, we also could have just have a one-dimensional table, which would be likely to be a goodness of fit test. But for tests like these, degrees of freedom is going to be rows minus 1 times columns minus 1. Make sure when you're calculating this, you don't count the totals. So we're going to cross out this row and this row. So we have 4 rows. Rows go across. Columns go up and down, just like columns in a building. So 4 minus 1 times 3 minus 1, 6 degrees of freedom. Next, we're going to be asked to find the expected value for the chi-square test, or for the cell value that has the smallest expected value. All right, so when we look at this, first off, the way we calculate an expected value for one of these cells is the row total times the column total. So let me go ahead and click this next one. All right, row total times column total divided by the grand total. So this cell that will have the smallest expected value is going to be the smallest combination of rows and columns. So like what I mean by that is when we look at all these row totals, the smallest one is 15, right? When we look at all the totals of annual income here, the smallest one is 47. So the smallest expected cell is going to be where those two intersect each other, and it'll be that value right there. So we're finding the expected value for that cell that has a 5 in it in the bottom left. Row total is 15, column total 47 out of 207. We get an expected value for that cell of 3.41. Lastly, it wants us to find the chi-square value for that cell. Chi-squared is observed minus expected squared divided by expected. This equation is in your equation sheet. So 5 is our observed minus that expected value that we just got. Square that difference because we want all of them to be positive, and then divide by the expected, and we get 0.741. The chi-square test statistic for the whole test is just going to be the sum of chi-square values for all the cells in this table. Now we're asked to use an inference procedure to verify the answer to the independence question in part C. It's also noting that the assumptions and conditions for inference have been met, which means we don't have to check them. So this is going to be a chi-square test of independence, which is pretty obvious because it's asking are the variables independent. And remember, when we do a hypothesis test for chi-square problems, instead of doing the full phantoms acronym, we're just doing HANTOMs. Okay, we can skip the parameter. And in this case, we're going to skip the assumption, the A also, because it's telling us that they've been met. So our null hypothesis is that age and income are independent. When you write these, make sure it's about all values and not just our sample. The alternative is that age and income are not independent. If we use the alternate wording, we would say for the null hypothesis that there is no association between age and income. No association. All right. And the alternative is that there is an association. This, as we mentioned, is a chi-square test of independence with 6 degrees of freedom. It's good to note that somewhere in your problem here. And we're going to go ahead and put this into our calculator. So we would go into the matrix menu, which I believe is above the math button on a TI-84. We plug in that matrix, and then in your list of stats problems, you're looking for chi-square test. On an 89, it's called a chi-square two-way test. So that'll give us a test statistic of 5.384, a p-value of 0.4955. Obviously, that's too big. We're going to fail to reject the null hypothesis because it's larger than 5%. And there is find that there's insufficient evidence to suggest that income and age are not independent. Remember, alternative. Our second sentence is always about that alternative hypothesis. Now, the reason it said on the previous slide that conditions weren't actually met is because I wanted us to do that test for the practice. But in actuality, one of the conditions wasn't met, and we really shouldn't have completed that hypothesis test. So the one that wasn't met was the expected counts condition. The conditions for this test are randomization, 10%, and expected counts. All of the cells should have an expected count of at least 5, and the one we checked there didn't. Okay, as soon as we find one that's not at least 5, we can say that that condition has been violated. Also a note, since this was the cell with the smallest expected value, is that it's really the only one we have to check. If we were to check that and get a value above 5, since this is the smallest expected value, all the other ones would be above 5 as well. Part G, if age and income were completely independent, find the number of 46 to 60-year-olds, you would expect to have an income over 50,000. So we're talking about this cell right here. We can see the observed, the actual count was 27. The expected count is calculated just like we would find an expected value for any of our other cells. So we would do row total times column total over grand total, and we get an expected value of 24.58. That's what we would get if these variables were actually independent. Now for our next problem stem, we have this spinner wheel here showing some numerical values, 100, 200, 500, and the word skunk there. So this is involved with a game where a contestant comes up, he spins the wheel. If he gets skunk, he doesn't win any money. The contestant's turn is finished. If he gets a number, that's how much money he's won. At that point, he can either stop and take those winnings, or he can spin another time. All right, and the same thing happens with the note that if a skunk comes up, he loses all of his money. and his turn ends. If he keeps spinning numbers, he keeps adding on to the amount 1 until he either chooses to stop or he spins and gets a skunk. So part A, what's the probability that the result will be a number on all 3 first spins of the wheel? Well, 3 out of these 4 sections there are values. We want to find the probability of getting not skunk 3 times in a row. So 3/4 times 3/4 times 3/4, 0.4219. Part B, suppose a contestant has earned $800 on his or her first 3 spins. They choose to spin the wheel again. What's the expected value, or the mean, of his or her total winnings for the 4 spins? So for this problem, we would want to make a probability distribution. All right, so up top here, I have the result of their upcoming 4th spin. They could get 100, 200, 500, or they could end up with a skunk here. All right, if they end up with skunk, they don't win any money. If they get any of these values here, it just adds on to the 800. So that's where these numbers come from. 900, 1000, 1300 is 800 plus the results of their last spin. Probability of each of those is 25%. And now we can just find the expected value or the mean by doing 900 times 0.25 plus 1000 times 0.25 plus those 2 multiplied plus those 2 multiplied, and it would total $800. A contestant who lost at this game alleges that the wheel is not fair. In order to check the fairness of the wheel, the data in the table were collected for 100 spins. Based on this data, can you conclude that the 4 outcomes on this wheel are not equally likely? So here we have a table again, but you can see that it's just a one-dimensional table. So we have frequencies for the results here, all right, but there's no other value. Like there's not another row of the table with additional variables. Once we have those like rows and columns, that's when it's going to be either a chi-square test of independence or homogeneity. When it's a single row or a single column table like this one, this will be a chi-square goodness of fit test. So we're going to run that full test, and again, we're going to skip the parameter. So our null hypothesis is that the distribution of wheel spins are uniformly distributed. Notice that I'm not saying the wheel spins in the table or the distribution of 100 wheel spins. I'm talking about all wheel spins. Okay, this is about the population, not the sample. The alternative is that the distribution is not uniformly distributed. One or more of these are going to come up in proportions that are larger or smaller than the others. Our conditions, randomization, the results of the wheel spins are assumed to be random. 100 spins is less than 10% of all potential wheel spins. And the expected cells, since we have 100 spins in our table here, and each of those spins is supposed to occur 25% of the time, we end up with expected values of 25 in each of those cells. So all of our expected cells are at least 5. As mentioned, this is a chi-square goodness of fit test. Degrees of freedom for a goodness of fit test are k minus 1, categories minus 1. So it's not 100 minus 1 like it would be for a one sample t-test, for example. It's the number of categories we have, which is 4, because that's not a category, minus 1, 3 degrees of freedom. We'll plug that into our calculator by putting in lists. We'll have these values in list 1, and then the expected values 25, 25, 25, 25 in list 2. Go down to chi-square GOF, goodness of fit test, and it'll give us that chi-square value and this p-value. Again, that p-value is too large. Fail to reject the null hypothesis because the p-value is larger than 5%. There is insufficient evidence to suggest that the distribution of wheel spins are not uniformly distributed.